7:30 p.m. Welcome everyone to the Steward Observatory Public Evening Lecture Series. It's hard to believe that it's been almost a year since we had our last public evening lecture. I quite often say at the introduction to these lectures that they started in September 1922, and we are very proud that since then, we have had public evening lectures every year since 1922, except for the 4 years of World War II, 1942 to 45. But then Pat Murphy reminded me that I'm also now going to have to say for most of calendar year 2020, because of the COVID-19 pandemic, we also didn't have any public evening lectures. As you logged on, you saw the schedule that we've put together for the spring. It's somewhat of a thematic schedule having to do with the search for extrasolar planets. We planned one lecture per month. Tonight's lecture will be an introduction to the topic. In 3 weeks on March the 8th, in conjunction with the mirror casting of the next segment of the Giant Magellan Telescope, Dr. Jared Males is going to tell us about how they plan to use the Giant Magellan Telescope to do adaptive optics to image extrasolar planets. And then Dr. Kevin Wagner will talk about a recent observations, recent work that he's had published on the topic in April, on April the 5th. Hopefully, we'll be able to invite everyone back to campus next September, but if any of you watched President Robbins' news conference this morning, we still don't know, even next fall, what state we will be in. It all depends on what happens with the pandemic. So we are very glad that you have joined us. I see that we now have 155 people. Hey, I guess the advantage is I'm not going to have to go to the back of the room and count heads. I actually have a count of how many people are logged on to watch the talk. I'd like to introduce tonight's speakers. Professor Daniel Apai is a professor here at Steward Observatory. You also have a joint appointment, I think, with the Lunar and Planetary Laboratory as well. Professor Apai received his education in Hungary. Daniel, where did you get your doctor's degree? From which institution?
It's the PhD I got from the University of Heidelberg in Germany.
Ah, schön. Yeah, University of Heidelberg. And your undergraduate degree was in Hungary.
That's right, yes.
And he will be joined by one of his graduate students, Jeremy Dietrich. Jeremy, where did you get your bachelor's degree?
I got mine from Harvard.
Harvard, all right. And Jeremy is now presently a graduate student here at Steward Observatory, the University of Arizona. So without further ado, I will turn everything over to Daniel and to Jeremy to give us a talk on the search for new worlds in the solar neighborhood. And there will be time for questions at the end of the talk.
Thank you very much, Tom, and thank you all for joining. This is great to see so many people, 160 of you joining. As Tom mentioned, today we have a special talk. We will be doing this together with Jeremy. We have some very exciting projects to tell you about. The work and the results that we will be speaking about is finding extrasolar planets, but also not just any planets, but planets that are very close to us, planets in the solar neighborhood. So in this talk, I will show you why these planets are interesting, what we know about them, what we don't know about them. And Jeremy will show a very exciting new method that we developed together and that allows us to find new worlds and predict where they may be. I wanted to start this talk with a big boom. This is a big boom by a SpaceX Falcon 9 rocket that in 2018, April 18th, carried NASA's TESS space telescope to space. TESS is NASA's only second exoplanet hunter space telescope. And in this talk, we will touch on both Kepler, the first one, and the currently active TESS. But before going to TESS and the science that it has yielded, I wanted to show you something that maybe not many know, and I think it's really cool about this mission. So in addition to the amazing science and the capable scientific cameras and telescopes that it has carried into space, TESS also carried with it a very small memory unit. In that memory unit, there were drawings. Let me show you some of these drawings. This is one. This is another one. These are drawings that were submitted by children from across the world. NASA asked them before the launch to imagine what words TESS is going to be able to discover. And children, more than 1,000 child across the country and across the world, took the time to sit down and think about and be part of this mission, drawing words that they have never seen before and trying to imagine what is that we may find there, how these planets would be different, but also similar to the ones that we have on our in our solar systems. And you see there were a variety of ideas, some more realistic than others. This is probably a very stinky planet, and others are surrounded by a ring system, probably resembling or Saturn. And this one is probably inspired by the storms that we may see on Jupiter. So we may think that these drawings are, of course, simplistic, but they, I think, convey two important messages. One is the excitement, the sheer excitement of being part of a really revolutionary exploration of nearby worlds. These are worlds nobody has ever seen before, and this mission is finding them. And then it is up to us to interpret, to figure out what these worlds are made of, how do they compare to our own world. This is, of course, a giant step for humanity because we have been imagining and thinking about whether or not planets may be possible and may be present around other stars really for thousands of years. But now we are at the era when we can actually answer this question and explore these worlds. And so just like the children's drawing, in fact, what we are finding is a great diversity. We don't find just clones of the solar system. In fact, as I show you, many of the planets that are typical in the solar system may not be typical at all around other stars. So this is one component, the excitement, I think, that is conveyed by these images. The second important point is that what did the kids draw? They basically drew planets that resemble the solar system with some changes. And this is pretty much where the science is today. We start from the planets that we know, the solar systems that we have been studying for hundreds of years, and then we try to compare to our worlds, the new worlds that we are finding. And we find differences, and then we try to understand what these differences mean, where they come from. So in the first half of the talk, I want to tell you a little bit more about the excitement that is not only represented or present in school children, but I think in probably all of us. And then move on to the actual science of exoplanets. So this is an image from, it's not of course by a child, but by an accomplished Hollywood artist or a team of artists. This is a spaceship called Avalon that was featured in 2016 movie Passengers. And this is really just one of the hundreds of movies I could have picked an image from, in which humanity in the future embarks on a journey traveling from one star, our own star, to the nearest star or nearest planetary system. The journey itself is going to be challenging. This is just one view of how these spaceships may look. Nevertheless, the fact that there is a possibility to travel in the far future to some of these planets, and it may be possible in some ways to come up with the right technology to do that, it really very much is an intimate part of the vision for humanity's future. So these are a couple of images from science fiction movies and novels that all relate to Tau Ceti, the closest sun-like star. And Jeremy will allow us to visit and take us to a journey within that planetary system as we know it. But you see that even specific planetary systems are very common in science fiction. We want to know what worlds exist around those stars, what their properties may be, and what may await us if we could ever travel there. So this is important not only in our imagination, but I like this quote from Stephen Hawking. He pointed out that if we think long-term, our only chance of long-term survival as a species is not to remain lurking on planet Earth, but to reach out into space. He says, I'm an optimist. If we can avoid disaster for the next 2 centuries, our species should be safe as we spread into space. And in fact, of course, the thinking here is that Earth has underwent many mass extinctions during its past history. And in fact, humanity is fragile enough that even extinctions that would not even amount to a mass extinction could obliterate our species. So there is definitely a value into moving beyond Earth to Mars, and then potentially even beyond the solar system. We are, of course, not there. Currently, we are at the age where we are opening our eyes to these new worlds, exploring them, and then trying to understand them. So I wanted to take a step back before TESS, jump back about 10 years, and take you to another launch. This is a launch of a Delta rocket, and this Delta rocket carried a much larger spacecraft to space than the relatively small but capable TESS. That spacecraft was called Kepler, named after the astronomer who understood, was a major player in understanding, a major thinker in understanding the structure of the solar system, and explained the motion of planets around the sun. And a very direct extension of that study, of that work, is to understand planets and using in part their motions and Kepler's laws, in fact, to around other stars. So the Kepler mission was launched and took a relatively simple but very powerful approach to search for planets. Now, this is maybe a good time for me to briefly touch on something that many of you probably know, why it took us thousands of years to get to the point where we can actually search for planets. The challenge here, of course, is planets, by definition, orbit stars. Stars are, by their very nature, much larger. For example, the sun is about 1 million times larger in volume than the Earth. It's much larger. And not only is much larger, it's much hotter. So it has a much larger surface area, a much higher temperature, and that translates to a much greater brightness. For example, if you would take an image of the sun and the Earth next to it, the sun would be 1 billion times brighter. 1 billion times brighter. That's an insane contrast difference. And that means that the Earth would be lost in the glow of the sun if you were to observe the solar system from outside. So we have to overcome that extreme contrast. And then again, there is also the problem of how close these objects appear when seen from a great distance. If you were to observe the solar system, the sun and the Earth would be extremely, even from a relatively nearby planetary system, the sun and the Earth would be very, very close to each other, making this contrast difference even greater. This is often compared to a case of trying to see a firefly that on a lighthouse. So what Kepler did and what TESS is doing and what we're doing in Project Eden, which I will touch on, is to actually circumvent this problem by looking basically at the shadow of these worlds, if you like. So what Kepler is doing and TESS is doing is what we call planetary transit search. They are looking at for events. We have a bit of a noise, so let me ask you if you are, please, mute your mics if you are not speaking, and then at the discussion you can unmute yourself. Thank you. So what planetary transits are events that occur when a planet passes between us and their host star. So this only happens in systems where the planetary orbits are in the line of sight, right? Not for every system, but if you look at a large enough number of planetary systems, you will see some in this orientation. So in fact, what Kepler did, Kepler observed for about 5 years 170,000 stars almost continuously, measuring their brightness, looking for these rare transit events when a planet passes in front of their host star. Now, Kepler, this space craft, was very patient, was able to do an enormous amount of measurements, intensity measurement, and indeed find a large number of planets. It increased the number of known planets by about a factor of 8. So not only it increased the number of planets, it also enabled us to detect planets that are much smaller than what we could detect previously. So the Kepler mission has brought in really a new revolution in our understanding of exoplanets, and it led to thousands of publications. I will not, of course, go through here the papers, not even the many of the important ones, but I do want to show 3 results from Kepler. 2 very simple, and the third very interesting. The first very obvious result from Kepler was that it has found over 4,000 extrasolar planets. So that's a huge number. I mentioned it's a factor of it more. And if you actually consider how many stars and planetary orbits we expect to be lining in the line of sight, so that Kepler could have been able to detect transits. Of course, about 99% of them would not have been in the line of sight. So if you correct for that, you actually find that essentially all stars in the Kepler field likely harbor planets. So again, around 99% of the stars Kepler could not have been able to see planets because the planetary orbits are not aligned. But just counting the planets that it could find and correcting for the what we call a detection bias, its inability to detect planets in many systems, we can calculate back how common planets are. And this is a fascinating and amazing result that does show that planets are very common in the universe. Now, this is something that we may have all suspected, but scientifically it was really not a done deal. Before Kepler was launched, we really did not know whether this would be the case. And in fact, those who study planet formation, and I've worked on that field also myself for over 2 decades, you actually need an astonishing number of pretty complicated steps to form planets. So many have argued that it's unlikely to happen around many stars. So the fact that we do find planets in a very large number shows that those steps, as complicated as they are, nevertheless, in a self-organizing manner, these planet-forming environments are able to carry out those steps, and those processes do result in planets very commonly. So that's very fascinating too, if you think about searching for life in the universe, right? Now we went from basically, in about 25 years, we went from a single known planetary system into a situation where we now know of 4,000 planetary systems. And if we extrapolate, we can expect that within the galaxy, there's probably 100 billion planetary systems. That's an amazing number. So there is a potential, we don't know for sure, but there's a potential that life could actually be common. That's very exciting. Now I want to show you a little bit, another result that I think was quite surprising for us astronomers, and one that is a little bit more involved. So I will show you a figure, and I think it's actually a really fun result. And this particular version comes from the original paper that showed this distribution, and I will explain this in detail. It comes from a group in California led by Fulton. This group used a Keck telescope to combine their data with the detections from Kepler and further refine the relative size of the planets. Now, let me just backtrack here a little bit. The way you can get size measurements for transiting planets is conceptually quite simple. So if I just play this animation again, where you see a planet passing in front of a disk of a star, you can see that part of the star's disk is covered by the planet. Now, it's very easy to imagine that if I would play this again, and this planet would be 3 times larger, it would cover 3 times as much area from the stellar disk. That would mean that the intensity drop that you would measure would be 3 times larger. So what this tells you is that if you measure the intensity drop by how much the star did get fainter. From that, you can easily calculate the relative size of the planet's size relative to its host star. So this is basically what was done in this Fulton et al. Study. And what you see here is a measurement where basically they plotted here on the x-axis. This is the size of the planet that they measured in units of Earth's radius. So Earth would be here. And on the y-axis is simply measuring how many planets are in a certain bin. Okay, so this, for example, shows you that for an average star, this size planet, for example, 1.2, 20% larger than Earth, this would be about 8%. And there's an uncertainty on these. The first measurements, and since then, this result has been refined, have better, less uncertain measurements, but the result did hold up. So this is a very interesting figure. Let me walk you through what this means to illustrate a little bit the process through which we entangle planet populations. So this is the radius of the Earth. And for comparison, let me plot here the sizes, relative sizes of planets. So you recognize this is our home, planet Earth. And to scale, this is Venus, Mercury, Mars, and Mercury. You can see that Earth is the largest, a little bit larger than Venus. On the right-hand side, there's a different scale, and here you can see how tiny Earth is when compared to Neptune, Uranus, Saturn, and Jupiter. So these are the gas giants, and these are often referred to as ice giants. And so our Earth is really just a small pebble compared to these guys. And the Sun, of course, would be even about 10 times larger in diameter than Jupiter. Okay, so let's contrast this, map this back to what we see here. So basically this 1.0 here, of course, would translate Earth. This is the size of Earth. And this is here the size of Neptune. In the solar system, there is no planet in size between Earth and Neptune. But we do have giants. Now, in the Kepler probed region, which was the inner planetary systems, interestingly, very few planets that are larger, so Jupiter would be here. There are very few planets, they are very rare, of the sizes of our gas giants. Really, the population, the number of planets starts to pick up when you reach Neptune and smaller sizes. Now, in the solar system, of course, we would have these larger planets and then Neptune, and then there would be a large gap in size, and it would only start to pick up at Earth and then smaller planets. So our solar system, in terms of size distribution of the planets, turns out to be unusual. In fact, there are two peaks that you can see here. One corresponds to planets that are smaller than Neptune, but significantly larger than Earth, so about 2.4, 2.5 times the radius of Earth. And then you can see a second peak rising here, and we now know that it continues to rise towards smaller planets. And Earth is a member of that population, which is basically peaking towards 1 Earth radius and potentially continues to rise further, but we have a poorer understanding of smaller planets. Okay, so what we learned from this is that we are actually missing probably the most common types of planets in the galaxy. We don't have these kind of planets and these kind of planets. Now, what are the natures of these worlds? We don't actually know. So the kids' drawings may be actually close. We start from thinking about Earth and how we could modify Earth to get to this population. And here the best example we have is Neptune. So we think about what is the best way to transform Neptune into these worlds like this. So we call these, for the time being, as mini Neptunes. And these planets' population, we name them super Earths just because they are larger than Earth. It doesn't mean they are better, they are just larger. So this is an interesting idea, and so it was a hypothesis we tested. The way you test hypotheses in science is that you make predictions, and then you carry out measurement to test those predictions to see whether your hypothesis was right. So here the idea is that if these are indeed mini Neptunes, in contrast to super Earths, then their composition should be different. So let me show you this it's a very simple measurement that we can make, and it was done. So we can use the density. So densities are basically the first measurements that tell you what is inside an object. Right? We all know that water, for example, is much lighter than a block of iron of the same size, and rock is intermediate. If you take a look and you calculate, or you can get from any textbook, the density of Earth, you will find that it's 5.5 grams per cubic centimeter. Okay, so it's a pretty small, like the size of a die or a dice, board game dice, would be about 5.5 grams. Neptune, however, is a much lower density. It's only 1.6 grams per cubic centimeter. So it's about roughly 3.2 times lower density. Now, we know what Earth is made of, and this is just a rough sketch of what Earth's interior consists of. Most of the large fraction of the mass, 31% of the mass, is in the iron core. Silicates, the mantle, make up about 63% of Earth's mass, and carbon, which we all use for life, is only less than much less than 1%, 5% of a percent. Interestingly, although Earth is often called an ocean planet, in reality, the ocean, the water, the total amount of water amounts to only 0.1%. Okay, so to the first order, Earth really is made of iron and silicates. If you account for these two components, then you are actually very close to the complete mass. And if you, in fact, calculate from this what density you expect, you get this 5.5. Now, when scientists went out to measure densities for these planet populations and some members of this planet population, they in fact found that these worlds had much lower densities. They were resembled in density much more Neptune than Earth, and these were here, everything that we could measure until now is very close to Earth's density, and it's far from Neptune's density, much lower density. So to the first order, this tells us that in fact, the population that we now call mini Neptunes are probably gaseous ice worlds and have low densities. And these worlds here, what we call super Earths, are much more resembling probably in bulk composition Earths made of rocks and iron. So this is a big step and an exciting step that basically just in a couple of years we could figure out that we are missing many of the most typical planets in the solar system, which just don't have these mini Neptune or super Earth examples. But we could get a crude understanding of how these planets may be. Now, interestingly, as people then focused on the question, why is there a valley here? And so this is a very interesting emerging story. This was not something that was expected by most scientists. We would have expected a smooth distribution and not a hole in the middle. It basically, what this figure tells us is that 1.8 Earth radius planets are missing. You can find many planets that are larger and many planets that are smaller, but this specific size of planets is missing. And so we have now a pretty good model that explains what's going on, and we are testing hypotheses and prediction hypotheses from corresponding to this model. And that model tells us that some of the planets here really started in this population. They were mini Neptunes, but they were close enough to their host stars that their upper atmosphere was evaporating. So they have been continuously losing gas from their upper atmospheres, and they moved to smaller and smaller sizes. Eventually, they move through this valley, basically you are removing planets from here and adding planets here to this peak as you are losing atmosphere. Now, planets that started very big with lots of gas, they still didn't lose their gas and they remained large. But planets that started with a relatively small amount of mass in gas, they lost that gas and then rapidly became an evaporated core. So this is quite interesting because we think if that is true, then this population of super Earths that are very common in the universe, they have at least two origins. One is an origin like Earth, formed from smaller bodies. But there is probably a large number of worlds that are super Earth-sized worlds that in fact are cores of evaporated mini Neptunes. So this is a fascinating new discovery just in a couple of, in the past few years. And then of course, now the big question is, can those worlds be habitable too? So this is something that many scientists, including us, are looking into. Now let me take a bit of a change gears here a little bit and tell you about our next steps. So Kepler itself was a statistical mission in nature. The goal was to get a good assessment of how frequent are planets of different sizes around different types of stars. How common are Earth-like planets around Sun-like stars? That was one of the drivers in Kepler. To do this, you need a large number of detections in a homogeneous sample. And when Kepler was launched, we really did not know whether planets are going to be very common or not. So what Kepler did to get this large number of transits, even though most of the planetary systems will not transit, it had to observe a large number of stars. To observe a large number of stars continuously, because you don't know when the transit is going to happen, you have to look at a patch in the sky where there's a high enough density of stars in the background that you can monitor a large number with the limited field of view of your camera. So in fact, Kepler did observe a limited field of view for 5 years, nearly 5 years, and this is that patch of the sky plotted above Kitt Peak National Observatory. So the good thing here from Kepler is that we did find thousands of planets. Limitation, however, is that in fact these planets are all very far away, thousands of light years away. Now our next step is, as a community, to look for planets that are in the solar neighborhood, because planets that are much closer to us are the right worlds that we can explore at a greater depth. They are very important because it is, as you can imagine, it's much, much easier to study a planet that we found that orbits only, say, 5 or 10 or 15 light years from us, than to study planets that are thousands of light years away. Therefore, the attention of astronomers over the past 4 years have turned increasingly to the solar neighborhood, to the stars that are the closest to us. And this is also a very nice overlap with the science fiction interest that I highlighted in the beginning. So what do we know about the even 50 light years? We know that there are about 1,560 stars, and there should be about 10,000 exoplanets. And maybe about 1,000 of these worlds could be similar to Earth. How many of these worlds we know today? We know of only about 104 out of the 10,000 that may be possibly there, even around the closest stars. And we found only approximately about 15 planets that are similar in size to Earth, out of potentially several thousand. And of planets that are similar in temperature, potentially, and size to Earth, we really only found 5, 7, and probably some of them will turn out to be less similar than we think. So we are really missing here over 99% of the worlds, even among the closest stars. So that's a fascinating direction. And this is basically why now you have 3 talks in the public lecture series that all focus on finding exoplanets around the closest stars. The talk today, I will touch very briefly on Project Eden, or search for the nearest star planets, and then alien Earth. And then there will be a talk next month by Jared Mills, who will show you how the next generation of extremely large telescope can be used to directly image those planets, not just look for shadows, but directly imaged. And then in a third talk, Kevin Wagner, who is also a member of my group, will show you some of our latest results using a very powerful facility in the southern hemisphere in Chile, aiming and targeting the closest star to us, Alpha Centauri. Okay, so very briefly, I will talk on Project Eden. I already gave, I think, 2 talks on Project Eden here over the past year, so I will not go into too much details here. But I did want to point out that we have a very exciting survey, Project Eden, which stands for Exoearth Discovery and Exploration Network, as you probably guessed. Our goal is to find and characterize habitable worlds within 50 light years. So we are looking for worlds that are yet unexplored, that are the closest to us. And we combine multiple detection techniques, but the primary one is looking for the planetary transits that I showed you. And I would just point out that this is an international partnership between Steward Observatory, the Max Planck Institute for Astronomy in Heidelberg, where I got my PhD from, and I have many good friends and colleagues, the Vatican Observatory, which is also as an office here in Steward Observatory, and Taiwan's National Central University. With these partners, we are able to span the globe and have telescopes on 3 continents that allow us to continuously monitor 24 hours when the weather is good above all our sites, the targeted stars. So that helps us to boost the chances that we are able to find new planets. And so these are a couple of examples of our telescopes that we are using. These are very exciting facilities. Many of them are in Arizona. So I will stop here now, and I will hand it over to Jeremy, who will show one of the powerful new methods we developed to help us guide our observations.
Thank you very much, Daniel, for that introduction. I'm going to start here in a little bit of a similar vein as where Daniel left off, and just show one of my favorite graphics, which is this plot showing the planets in the solar neighborhood. These rings here are 15 and 30 or so light years. And you can see all the different crazy planet systems, 7 planet systems, 8, 4, 5, 6, lots of planets we know about. But again, these are only the planets we know about. There, as Daniel mentioned, there was a ton of stars where we'd expect to see planets, and yet we don't see all those planets. So where are the planets? Well, they're likely hidden, as he's mentioned. We can only see certain planets due to the limits of our observations, the detection biases we see. So I have a very simple graphic to show that as well. We would see that planet transiting in front of its star. We would see the light curve, the light from that star dip as the planet goes in front of it. So light goes down and goes back up again. However, if the planet orbits at a slightly different angle, and it goes down this way as it orbits, we wouldn't see that planet. We would have no direct evidence via the light curve that that planet exists. However, we do know that planets likely exist where we cannot see them. Somewhere out beyond these known planets, there probably are other planets out there existing. Well, how do we know that? It's not magic, it's math and statistics. Put it another way, can we use the currently known planets to find new additional planets that we don't yet know exist? We understand planet populations to a pretty good degree. And a large majority of that is due to Kepler Space Telescope, as Daniel mentioned. It provided thousands of planets from which we could learn numerous data points from each of these planets. This here is an illustration of it with multiple different types of planets that it might have found. An artist's illustration, of course. We don't know quite exactly what they look like. So in order to answer this question of can we use planets to find new planets, Daniel and I created the DYNAmical Multi-Planet Injection Tester, which we shortened to DYNAMITE. So it's a Python software package that the two of us developed over the past year. Using it, we can analyze multi-planet systems to predict the presence and location of additional planets in a system. So if we see, very nicely ordered planets in a system, and then all of a sudden there's a big gap between a planet and between 2 planets, we would likely think, there might be another planet there we're missing. We just don't see it because, something's off on the orbit. We can also evaluate the different sizes that any of those planets could be. We have data on each of the planet sizes there, and maybe we can find out what the average planet size would be and use that. We can also assess the possibility, and my favorite part of this, of finding an Earth-like planet, a rocky planet orbiting far enough from its star where water would be liquid on its surface. Maybe it would also have some sort of an atmosphere in order to keep it warm. So some sort of potentially habitable planet. We can determine the likelihood of finding one of those. That would be really interesting. The DYNAMITE is an open source software package. It's freely downloadable from GitHub. And it's updated and refined as we learn more from all the different exoplanets that we keep discovering. It's already being used to support the search for and the confirmation of exoplanets specifically in nearby systems. And it boils down to a recipe of 3 main components. The first is we gather very specific data from each exoplanet system that we're trying to analyze. So from that, we can gather planet parameters. For each planet in the system, we know its orbital period, how long 1 year takes on that system for that planet, what its size is, radius or mass, depending on what observation technique we use to discover it. We also know a lot about the stars themselves. We know their size, radius, and mass as well. We can determine their temperature. We can even, for some of them, determine their rotation period and their age. Astronomers have been studying these stars for decades, so we can gather up all this information and have a very comprehensive list of information that we do know. This is all actually, carried together and collated in the NASA Exoplanet Archive. And you can see that just by looking at the size of the scroll bars on the right side and the bottom side, just how much data that they already have contained in there. And they actually show, that they have records for 4,341 exoplanets, and that number is increasing constantly. There's always new planets found and always new things confirmed as the days go by. However, it is unfortunately a bit incomplete. You can see that there are gaps, especially in the sizes of the planets, sometimes even in the orbital period or distance, how circular or non-circular the orbit is, what the temperature on those planets are. We can get that data for some of them, but not for all. So our census of these planets is incomplete. But that is where we're really trying to figure out how we can find more. We have this specific incomplete data set. Can we make that data set more complete by finding additional planets and characterizing them? So the second ingredient is basically a combination of the general data from all the systems, across all systems of exoplanets. We can use those, the entire population, to infer basic general properties. So, for example, we can figure out where planets are most likely to be found, at what period, how long they're going to orbit, and then also what the relative sizes of planets in a system are. So we can, if we know what the current size of the planets are, we can maybe predict what the next one will be. So this comes in from population statistics. It's a little scientific term, but from these populations of planets, from all the planets, say, that Kepler discovered, we can look for trends in the data. So as an example, we can try to find the innermost planet in the system, and we can find the usual position of that by averaging the orbital periods for the shortest period planet in each system. So if we tend to find that the shortest period planet, the first planet in the system, is at 10 days orbital period, then that's probably likely to be true for most systems as we discover them, that the first planet might be at 10 days. And so as you get into large data sets, as you get to data sets that are multiple thousands of systems in size, the general difference you're going to notice between any specific system of planets and the average value across all the planets tends to be small. And this defines the population distribution, the distribution of values for that parameter. And from this distribution, for each parameter, we can determine what the most likely values are, which then get placed into our predictions for future planets. So some of the trends we've been looking at as part of this software package are position of planets. And so planets can be equally spaced or clustered together. We found that both of those can exist. There's not enough data yet to really fully determine if either of those are right, so we test both of them. Here is a very simple illustration of planets relatively equally spaced in orbit. We find that planet sizes in a system tend to be correlated. So this is an artist's impression of the 7 planets in the TRAPPIST-1 system. They're all, likely rocky planets, roughly Earth size. Some of them are slightly smaller than Earth, some of them are slightly larger than Earth, but they all tend to be roughly the same size. And so that's a trend we actually find in a lot of systems to date. And then planets in a system tend to orbit their host star at similar angles. So that's why we can see them as they pass in front of their star. They all tend to orbit. The ones that we do see tend to orbit in that same angle. So this is a video, one of my favorite videos I saw of the TRAPPIST-1 planetary orbits. So this is a 7-planet system, about 5 parsecs away. And this visualization right here shows the data that was taken to show the transits, those dips in the light that are marked by the letters of each planet. And then the top shows what we would look at, what we would see if we could actually determine, actually look at the star and watch the planets as they orbit it. And so you can see planet B zipping around there really quickly, and you can constantly see it showing up. And then C comes around a little bit slower, and D slower than that. But you can see that they all orbit at, pretty similar angles. They're all, in our line of sight. And so those are the planets we can find. The ones we can't find are the ones that don't follow along those lines. So the last ingredient is the stability of these planet orbits. And so the stability of any two planets tends to be determined by the distance between the planets, and as well as the masses of the planets themselves, because the main perturbing force these planets would put on each other is gravity. So gravity is stronger when planets are closer together and when they're more massive. And so if they're too close, or too massive and too close, then they can interrupt each other's orbits and fling each other out of their stellar system. So I have a couple of videos, again, little handmade ones to show that. So I put together a few roughly equal mass planets and orbiting roughly equally spaced, and I just, under the influence of gravity around their host star, this is how they would orbit. And so you can see that they, have a nice even circular orbit, and they don't necessarily have too strong interactions. And this is over a short period of time, but this actually does stay stable for millions of years, which is good because we're looking for planets on timescale. Their ages are usually millions to billions of years. Now, however, I moved the third planet much closer, almost right on top of the second planet, a little bit for exaggeration to show this exact feature. But when I start doing that, whoop, that planet just disappears. It gets thrown out of the system as it interacts with the two planets close to it. Show it again, and it just goes, okay, I'm gone. What actually ends up happening much later is that the second planet also gets thrown out because it interacts with the first planet in this area here where their orbits get really close. And so if we were to observe this millions of years later, we would only see 3 planets there. So we know that that's how we know that planets can't get too close, otherwise their orbits will be interrupted by their influences on each other. So from these 3 ingredients, we come together and we create testable predictions. So we can utilize the current knowledge that we have from those, all the data we've gathered to predict what a planet would look like in that system, any additional planet, and what its characteristics would be, what its size would be, how long its orbital year would be, etc. And then we turn these characteristics into observable measurements. So we have a planet with a predicted size, and we can say, okay, if it's highly likely to transit, then we can determine the transit depth, as mentioned before, by knowing the difference in size between the planet and the star. However, even if it's a very low probability of transiting, we actually can still measure the stellar motion due to the planet tugging on it in its orbit as it goes around its star. Now, if there are multiple planets, there'll be multiple tugs, but we can still subtract out all the ones we know and then determine if there's still any leftover movement that might be caused by another planet. And that's the sort of level of focused follow-up observations, like Project Eden staring at a bunch of stars and trying to find those transits that we can do to try to find these additional hidden planets that are missing. So DYNAMITE does all this together, and we tested it for the first time by using it on a system where we ourselves removed a planet from the system that we knew existed, and to try to determine whether or not we could find it again. So for the Kepler 154 system, the 154th system confirmed to have planets by the Kepler Space Telescope, we removed a planet with a period of about 10 days. So you can see here in this graph, the green planets are the planets that exist and are known in the system, known by the analysis to be in the system. The X is where the planet had been that we removed. So DYNAMITE has no knowledge of there being a planet there. However, it still reproduces the fact that the planet does exist. And so there's a very high probability of finding a planet in an orbital period of, say, 9 or 10 days in that system. The next one we could find if we had another one planet there would be out about 100 days if you continue this chain of planets further out. So not only can we measure, predict where the planet might be, we can also predict if it's likely to transit and what its size would be. And so this is again that same planet that we removed, the 10-day planet that we removed. We have the planet period, or the planet radius and orbital angle in red here, and so it's slightly larger than the Earth, and it definitely does transit. It's very close to being almost directly edge on at 90 degrees. And DYNAMITE was able to reproduce it fairly accurately. It didn't say that it was a Neptune-sized planet that didn't transit if it was down in the bottom right part of this plot. It was, well within reasonable size. It was slightly larger and slightly more edge on, so slightly more likely to transit, which we did end up saying, yes, it does transit. We know it does. So DYNAMITE was able to reproduce very quickly and very easily these known planet parameters for a planet that we removed from the system. And so, TESS, the mission shown here in another artist illustration, has found over 2,000 planet candidates already, and they started confirming them pretty recently. And so we ran DYNAMITE on a subset of those test systems, and we found that there's a bunch of places where an additional planet could likely be found. This is a plot from our paper from 2020 showing where the red dots are the planets based on their sizes, and then the blue shaded areas are where we'd highly expect to see another planet. And from this, already evidence has already been compiled for the presence and existence of a couple of our predicted planets in these plots. So now I'm going to move on to our famous case study that we've done with this, and that's something that was already mentioned previously from our second paper on the subject, which is Tau Ceti. Tau Ceti, the background image you're seeing here is actually an artist's illustration of the Raman node, which is from Arthur C. Clarke's Rendezvous with Rama series. The Raman node was a way station for interstellar travelers, extraterrestrial, highly intelligent beings. As they traveled the galaxy, this was one place where they kind of stopped to, upload and download information, get their coordinates and their trajectories and head off to another system. And so it's a very famous system in terms of science fiction, but it is the closest single-like star to us. It's about 12 light years away, so the Alpha Centauri system is closer, but it's a multiple stellar system. There's 3 stars there. Tau Ceti is a single star. It's just like the sun. There's no close neighbors. It's the only one there. So it's been known for a century almost that it was extremely similar to our sun. It also hosts 4 confirmed planets, as well as 3 unconfirmed planet candidates. So it's a very large planet system, also very similar to our solar system. And as shown earlier, and it's home to many science fiction human outposts. So there's the Nauvoo from the recent series, The Expanse, was a generational ship meant to start a human colony in the Tau Ceti system. If you go back, a few years or a few decades, and you have Captain Picard of Starfleet, he used to frequent an exotic bar in the Tau Ceti system during the run of the TV show Star Trek. And if you want to go even further back, then there's Barbarella, whose spaceship crashed on a planet in the Tau Ceti system. So it's extremely popular for science fiction because of its similarity to the sun. So here's a video that Daniel Apai helped make that I'm going to do a couple snippets of this, describing the Tau Ceti system and what our analysis has shown for it. So here we have the habitable zone, the area where the water would likely be liquid on the surface, here shown in blue. And then here are 3 of the 4 planets that orbit inside the system. We see the 2 planets get pretty close there, but they are not massive enough to really disrupt each other's orbits. So there's 3 interior to the habitable zone, where it would be very hot, and 1 exterior to the habitable zone where it would be very cold. And so, these 4 planets are the ones that there's confirmed evidence for. But as of now, or as of when this came out, there had been no planet yet detected within the habitable zone of Tau Ceti. So we were able to run our analysis on it. And so the DYNAMITE analysis of Tau Ceti showed this. We found predictions for 4 planets, additional planets in that system. Remarkably, 3 of those predicted planets matched very well with the positions of the unconfirmed planet candidates. So here we show the unconfirmed candidates as the yellow diamonds, And then our predictions in the blue here match up very well with those. And the known planets are shown here in the green triangles. However, the most exciting part, I think, is that there's evidence for a possible 8th planet in the system, which we call predicted exoplanet 4, because we predict 3 other ones interior to that just happen to match B, C, and D. This is the 4th one we predict, and there's no counterpart to it yet. All the evidence of all the different planets in the system are pointing to the fact that there should be a planet there. But we don't yet know of one that exists. And it is right in the center of the habitable zone for Ceti. So if there were water on its surface, it would be liquid. So here again is another snippet from that same video where we discussed that, and we add in the 3 inner planets. So you can see it gets really tightly packed in there. But again, the planets are, only slightly more massive than Earth or Neptune, and so they're just, still stable as they orbit. So here's the 6 planets interior and the 1 planet exterior. And then we predict to be 1 extra planet right there in the habitable zone. So we call it PXP4 because it's the 4th one that we predicted outside of the ones we already know that exist. And so our analysis can also predict the nature of the planets in the system. So we have, planet mass here on the x-axis, and we have the likely masses for each of the 7 planets in the system shown here, or 4 planets and 3 candidates. And so we find that there's a good possibility that the planets could be rocky, as these would be rocky planets in this area. Anything out in here would be starting to get into Neptune mass planets or sub-Neptune mass planets, where we might expect to see things that are, as shown earlier, would have a large gaseous atmosphere of sorts. But these ones could be rocky and could therefore, have a solid surface for which there could be, basically, we're looking for life. We look for things on a solid surface. So this is extremely exciting that any additional planet in this system has a very good possibility of being rocky. And we did a slightly different analysis of the system to check all of our bases. And we found that, again, there's still very good support for the 3 planets, 3-planet candidates that have yet been confirmed. It does also find a high probability of an additional planet, but it shifts it much further out in the habitable zone. Interestingly enough, if we continue this and and try to run it again, inserting all those planets, it yet finds another possible planet, which we call PXP5, that could orbit in the habitable zone as well. So Ceti could possibly host up to 9 or even more planets beyond planet F, but it could also host 1 to 2 possibly rocky planets within the habitable zone of the star. And so that might turn some of our science fiction stories and our wild hypotheses that could exist here into science fact. We may end up finding that there could be a planet here that could host life in some way, shape, or form. So we know the planets are out there, right? We know that most stars likely have multiple planets. We know that we just can't seem to find all of them because they're hidden. There's some mechanisms, either their orbital angles, or they're just it takes so long to discover them that we just don't know of how many there are. And yeah, around 95% of exoplanets in nearby systems may not yet be known. And throughout the whole galaxy, we're missing 99.999% of all of them because we just can't observe all the stars in the galaxy for these things. But we want to use the future of DYNAMITE to continue to look for these planets. So we expect to find at least 50 previously hidden planets within the closest 50 light years to the sun. And so we're hoping that we can use this to also look for the longer period planets and the larger planets. Right now we're kind of stuck. The population is, as shown earlier, mostly these mini Neptunes and these super Earths. But it'd also be really cool if we could look for these Jupiter-type planets that are on much longer orbits and much larger planets. Basically, in general, we just want to increase the detection efficiency for all types of planets, whether it be Earth-type planets, Mercury-type planets, Jupiter-type planets, Neptune-type planets. However far they're orbiting from the sun, however large they are, we want to be able to go find them. But we really, really would like to discover a planet super similar to Earth, right? We'd like to have a rocky planet in the temperate zone, liquid water, possibly, water would be liquid on its surface. That would be a great place to start trying to super characterize that planet and look for signs of life from its light. So, as a conclusion, we know many planets do remain hidden, but DYNAMITE can help us find them. And so from there, I will send it back to Daniel for the final bit of the talk.
Thank you, Jeremy.
And I just want to point out it's 8:30, Daniel.
Yes, thank you. I just wanted to end the talk by just mentioning one thing that we are very excited about, and you will hear more about this. So over the past 2 years, we have been preparing a major proposal to NASA to seek funding for University of Arizona-based team to take the studies we are carrying out to the next level. So DYNAMITE is part of that, Eden is part of that, other projects too. We set out to, and we proposed to NASA to put together a large team and fund a large team to answer the question, which nearby planetary system likely to host habitable planets and life? And so I'm very happy to tell you, and there was a press release a short while ago that NASA selected our proposal for funding. So this is a very large project that we are launching now. There will be an official launch event probably in early April, and we are planning to organize an online event for that. And we will all let you all know and invite, and hopefully that you will participate. It's a uniquely large program in that it to answer this question, we will and we have built a team of 45 scientists from 11 institutions from 7 countries. And NASA is funding our team for 5 years with $6 million. All the money stays in the US, and most of it comes to the University of Arizona, but we have international partners who bring their own contributions to the table. So this is a really fascinating project. We have 14 sub-projects here, and we will be combining or advancing our knowledge of planet formations, how planets form, and combine these with assessment of habitability of planets that are out there, threats that may destroy these worlds, and then combine them, this integrated knowledge, and use that to guide NASA missions that are in the planning towards an ability to towards a search for signatures of life around these worlds. So for the next 6 years or so, you will see lots of results emerging from this team. So I wanted to end the talk just by bringing you back to the very first slide I started with, these drawings of extrasolar planets by children. I think that really conveys the excitement that we all feel about exploring these new worlds. And I hope that Jeremy and I were able to show you how science then complements the curiosity and the excitement that we all feel into transforming these drawings into actual facts and a known understanding of the new worlds that are surrounding the solar system. Thank you all.
All right, thank you so much, Jeremy and Daniel. I just wanted to comment that hearing about DYNAMITE reminds me a lot of how the planet Neptune itself was discovered in 1845. Leverrier used the orbital parameters of Uranus to predict there should be a planet beyond Uranus. Galle looked where Leverrier said it should be, and within half an hour he found Neptune. It's basically the same process. So we have time for questions. I'm actually I see in the chat a couple of questions that have been typed in. So why don't we start with those? Richard Spitzer says, seems to be a bias of finding planets close to stars. Could we find most of the planets in our system if we were 50 light years away? And then Todd is even asking, has DYNAMITE been run on our solar system as a check? For example, yes. Does it predict a planet at the asteroid belt?
These are excellent questions. So maybe I take the first one, and then I let Jeremy answer the second one. So Yes. So depending on, it's about the ease of finding planets that around stars that are close versus planets that are far away. So there are different methods to you can find planets. Today we spoke about the planetary transit method, and there are other methods too. You will hear talks, for example, about direct imaging. Direct imaging aims to spatially separate the light of the planet from the light of the star and take an image where you can see the planet. That method really only works for the closest stars, and that has a very strong bias with the distance. Planetary transits, which currently have produced the largest number of planets, however, they just rely on pure intensity measurement, brightness measurements. And in fact, those are more efficient for stars that are far away, typically, because it allows you can measure many stars at the same time. Whereas with direct imaging, you have to look at the closest stars, and you can sample one star at a time, and you need a much more complicated technology to separate the light. So finding that's around close versus nearby stars, different methods have different biases. Right now, actually finding the solar system and completely mapping the solar system would be pretty challenging. So most planets in the solar system would remain very difficult to detect with present-day technology. Let me go to Jeremy, who can answer the second question. And we have been DYNAMITE in the solar system, and very good question.
Yes, so I actually have run DYNAMITE on the inner solar system, at least. We have an idea of, at least out to Jupiter, what the likely places we would find, the statistics at least to corroborate our findings for that. And yes, DYNAMITE does expect there to be a planet at the position of the asteroid belt. Now, what happened likely is that we lost enough material there from the early formation parts of the solar system, and we probably lost the ability to form a planet there. But we do at least have a debris disk showing that there was some large mass at that position, which under other circumstances might have formed a planet. DYNAMITE also actually predicts at least one, possibly multiple planets interior to Mercury. Mostly because the solar system is a large outlier in terms of the fact that Mercury, being our first planet, orbits at 88 days, which so it has one full year in that period of time, which is about 8 times longer than the average for any other stellar system, exoplanet system. So DYNAMITE expects to find at least one, if not multiple planets, filling in that gap between where Mercury is now and where the average planet system would be. That could be evidence for something happening, early in the solar system's lifetime that scattered those inner planets, either into the sun or out away from the solar system, or it could just mean that we ended up forming in a very odd way that we don't fully quite understand yet.
Okay, Bill McGregor asks, how and to what extent will the Giant Magellan Telescope be able to support observations to confirm predictions made by DYNAMITE?
It's a great question. So, and I'm actually involved in the GMT project, which is a very fantastic project. And Jared Males will speak about that more in detail. But DYNAMITE's, the most relevant predictions from DYNAMITE for GMT will be the closest system. So GMT will be very powerful in combining all of its mirrors to act like a single large mirror. And with that, take super sharp images that can separate the light of the planet from its host star. So GMT will, with DYNAMITE, we may be able to predict where GMT should be looking for planets around the nearest stars. And then GMT will be able to take those images and then revisit the system a few weeks or a few months later to watch those planets orbit around their host stars. And so that will be a really nice verification and test of the DYNAMITE predictions.
All right, Sid Leach asks, does DYNAMITE assume that planets form in the orbits where we find them now and do not migrate in towards their star?
Yeah, that's a very good question. So right now, DYNAMITE actually doesn't have an assumption on the planet formation itself. We basically assume that where it is now is where it has been for a long period of time, and that it will continue to stay there for a long period of time, which is generally the case for most exoplanet systems we know. It is possible, it is one of the things we're looking at in the future as one of our expansions, to incorporate planet formation models and to determine and discuss how, what we would see if we started out with certain planets being formed and then migrating inward, or, and other, consequences of that, and see whether or not we can reproduce what we see from that data, and then if there are additional planets that we don't see from there as well.
Okay, we have a comment and a question from Daniel. He comments that this is an excellent presentation. He wants to know if you have any thoughts on solar geoengineering to control climate change as endorsed by the Bill and Melinda Gates Foundation. I know that's a little bit off the topic of today's talk, but did you want to make any comments about that?
I think that's a fascinating possibility, and I think it's a big topic. I think it's very interesting to look into and potentially as an emergency solution, it may have a role play in the future. But of course, there are a lot of ethical issues, practical issues. I did read some books about it, so I have lots of thoughts, but I think that's a big topic.
Daniel, Allison Hughes asks, she says, you opened this lecture with the Stephen Hawking quote about our species survival. Do you agree with him?
I would think that extrapolating from where we are now, which is always has its dangers, but I would think that right now with what we know, Stephen Hawking is right. And I do think that for the future, long-term, if you think long-term about humanity's future, it is important to leave the planet.
Okay, and we have an interesting question here from Steve Peterson. He wants to know if you have any professional amateur collaborations currently available for amateurs.
Sorry.
Go ahead. He says he regularly observes exoplanet transits using differential photometry at his observatory in Vail, Arizona.
Yeah, so that's a great question. And so we are interested in working with amateur astronomers, absolutely. And so Project Eden, in fact, using telescopes that are intermediate and small size, we built a large network. So Steve, if you have interest in potentially working with us, we would be very happy to get in touch. And maybe if you let me invite you to drop me an email, maybe, and then could follow up.
Daniel's email is Apai, A-P-A-I, at email.arizona.edu. And that seems to be the end of the questions. And we thank you very much for your presentation, Dr. Apai and soon to be Dr. Dietrich. I will remind you that our next talk will be 3 weeks from today on the 8th of March, when we'll hear from Dr. Jared Males about the Giant Magellan Telescope and the adaptive optic system that we intend to have on that great telescope. So I wish you all a pleasant evening from Steward Observatory.
Thank you, Tom, and thank you, everyone.